hello everyone once again. So I'd just like to welcome you to this panel, where the question is, what do the next 5 years of AI look like? And of course, AI is going to be, well, is already one of the biggest, if not the biggest, things, revolutions in our lives, and it will be for the next several years and decades to come. And so it's particularly important that we're all up to date and have the best advice from the world experts. And so we're very lucky to have the set of people that we have here today. So thank you very much first. And so I'm just going to give a very short introduction to each person, and then they will elaborate on it themselves. So we have Jakob here on the end, who is a professor at Oxford and works at Meta AI as well. Feryal, who's a research scientist at DeepMind. Katie, who's a PhD student at Cambridge and the Alan Turing Institute. We have David, who's a machine learning researcher at XCX Markets. And you can see that Elena looks somewhat different today, who is now Felix, who is at Harvard and MIT studying more cognitive science. And so many thanks to you all for coming today. Just a quick round of applause for them being here. And so if I could just start with Jakob and have 1 minute or so, just elaborate on yourself and what your approach to AI is.
Yeah, so, this is really loud. First of all, thank you for being here. Thanks for having me. I started doing machine learning long before it was cool. And my goal has always been try and find the hardest problem that seemed just about impossible and try and pursue them across different institutions with people who are smart. And what this meant in the past is trying to do multi-agent learning, having agents that come up with their own communication protocols, because I thought language was key to success, to intelligence. Looking back, that was true. Language was key to success. The approach we took at the time as PhD students maybe wasn't the right one. Maybe we should have instead pre-trained large language models from open source, from the internet. And now I'm trying to learn from my lessons and try and build the next generation of AI systems. So my key question to all of you is, where is the current wave going to saturate and what happens next? And that is the leading question that motivates me, that gets me out of bed, and that lets me drive research teams and projects across institutions.
Yeah, okay. My name is Feryal, and I'm a research scientist at DeepMind, and I've been thinking a lot about reinforcement learning throughout my career, and kind of really excited about this kind of interaction with the environment and this grounding that comes from interaction with the environment. And it was just fascinating to me, how can we learn just from kind of feedback from the environment? And of course, when kind of the foundation model, kind of the whole thing exploded, and we saw that actually from learning from just vast amount of data, we could get a lot of interesting, rich behavior that we didn't expect, like all this grounding that comes without even needing to interact with the environment. So that was really fascinating and surprising to me. So it really shocked me and made me question a lot of kind of beliefs that I had around kind of the importance of reinforcement learning. But actually, like, the more kind of I switched my research a little bit, kind of try to understand kind of generative modeling and how this kind of connects back to reinforcement learning. And I actually believe that we just have a better starting point for reinforcement learning, and we can now tackle much more challenging problems. And I really think going beyond, kind of as you were saying, where does this data, kind of learning purely from data saturates, and now if you want to go from more complex problems and problems that requires kind of maybe actually going beyond even language, like multimodal and kind of more agent-oriented tasks where you need to communicate with other agents to solve a task, and all of this brings back needing to learn from interacting with other agents and learning through reinforcement. So still, I'm very excited, and I've been working a lot on this, trying to kind of supercharge basically the foundation model to self-improve and kind of learn to go beyond the data that they were training on.
And I'm Katie. I'm a final year PhD student at Cambridge, and my undergrad was in cognitive science. I've since kind of moved back and forth between cognitive science and AI. And the question that excites me most right now is how we can build AI systems that really meet our expectations and complement our limitations. You can imagine building a system that kind of is superhuman in many different ways and can operate at such faster speeds than us, but at the same time, if we can't predict its behavior, is that really going to be an effective AI assistant? In contrast, you could build a system that kind of works exactly like a person and is very human-inspired, but that might not really complement our limitations in the ways that we could if we kind of use the full power of AI. So I'm very interested in kind of how to navigate that trade-off.
I'm David. I did a PhD in pure math a long time ago, worked in a psychiatry department for a while doing computational neuroscience, drifted into machine learning, was at DeepMind for a while, and now I'm doing algorithmic trading at XTX markets. I can't talk too much about what I do at XTX because it's just a very secretive world, but I'm going to talk a bit about data in a bit, but one thing I want to emphasize about our current moment is just how simple everything's become. So, modern machine learning is basically just matmos, so very basic linear algebra, backprop, so just differentiation, and we construct loss functions by averaging. And that's kind of 95% of what's going on. So it's gotten very simple, and it's quite a beautiful moment for, I think, science in general, that this very simple language is spreading in more and more places. And that's what I'll talk about in a bit.
Hey, I'm Felix, also a final year PhD student between Harvard and MIT. I've jumped across the pond in AI a couple times now. I started off originally in undergrad like 8-9 years ago with Ken Stanley doing evolutionary computation, and the goal there was to, let's mimic everything all the way from evolution all the way down to what's being evolved. And through that experience, I kind of shifted my perspective into more recently realizing that I think the right way forward is to think about human intelligence first and reverse engineer from there. And then once you have that sort of basis set of how humans work, generalize into more, general applications of intelligence.
Okay, super. So a diverse set of people with a diverse set of backgrounds. And so now I'm going to ask, again in order, the question of what do you think are the most fundamental questions, the most promising directions, and what we should not be doing, or should not be doing. And I said in order, but please at this point feel free to jump in and correct someone else and go out of order. Just get it going.
Awesome, yeah. So there's two parts to this. First of all, what do I think will happen in the next 5 years? We will be patching up all of the fundamental shortcomings that make our current wave of technology basically brittle and inappropriate for strong AI. We'll be working around the fundamental limitations in a way that gives us myopic progress. What I mean by that is we'll still use the same paradigm of large-scale pre-training, all the data you can get, and then it breaks this, and this, and then we'll collect custom data, fine-tune it, and so on and so forth. Why do we do this? Because it gives us incremental improvements. So this is what's going to happen because it's useful. These things you can build at that point can already be deployed because you can solve problems you couldn't solve before, and there's going to be money to be made, and there's a lot of GPUs to be bored, and cycles to be spun, and papers to be written. I took this custom model, this huge off-the-shelf model, I collected custom data, and can now do this thing that you couldn't do before. That's a paper, right? We also make zero progress in method, in understanding, or science at all. So while I'm saying this will be happening, I'm also advocating we shouldn't be doing this. We should leave this job to people who aren't able to come up with anything better. And I want to encourage all of you in this room to instead go and be the future. Don't play catch-up. Don't wonder what did OpenAI do to patch up this thing recently. The reason it was hard to build O1 and Strawberry is because these models are bad. Right? It's not because you shouldn't be a genius to get this machine to do useful thinking. Does that make sense? So I'm encouraging all of you, don't play catch-up. Think ahead. Where's this wave going to end? What are going to be the problems that will still be open at that point once we run out of willingness to pay for human data? And let's fix those problems.
If I can ask a question, then what is your approach to fixing those questions? Which are the directions you're going?
Well, for example, I can throw one thing out there. Our systems today are way too sample inefficient. There's no way I should be needing 2 trillion tokens, right? There's no way on earth I've consumed that number of tokens. So let's optimize for sample efficient models and go back to pre-training and think about sample efficient pre-training. And the good news is this is actually a direction that, for example, academia and startups can be pursuing because by definition, you don't need a lot of data and you don't need that much compute. So, for example, I'm saying, let's go back and think about what is intelligence, is generalization, what is not memorization, how to know the difference, sample efficiency and compression is the root of intelligence. Let's double down on that direction as a community and go and leapfrog. Let's make it so that all the people with the trillions of dollars of GPUs are left in the dust because they can just write all of them off.
Well, what better to have DeepMind respond to that? Okay.
Wow. No
Nice.
pressure. So I agree and disagree with some of the things you're saying. So I
That's what I'm here for.
Yeah, exactly. So I do think diversifying our approaches to answering some of these questions is really, really important, like not doing the same thing, all of us. And I feel like the field has gone through what you're saying, that everybody's jumping on the same train, and I think that's very bad for the field. I really agree with your perspective on efficient learning. I mean, my take is a little bit different. I think that from any starting point, it doesn't matter if it's a foundation model, if you have access to, or like a smaller model, we want efficient algorithms to learn from new data. So whatever model you have, don't throw it away, because you could, kind of have a better starting point, but we want algorithms that, given any starting point, can learn very efficiently from new piece of data. So that really fascinates me. For example, if you could interact with a user and learn very quickly about their interactions and remember that through time. And for that, we need better kind of online algorithms, meta learning, like learning to learn, and like discovering these learning algorithms that are really quick, because we are all, kind of the algorithms we right now have are very, very inefficient, both in reinforcement learning, supervised learning, everything. So I do think that's really, really interesting. I agree that you could investigate those in any scale, both at the large scale or small scale, and that could be really cool. And I think, in terms of what I'm excited about is exactly this question, and also like what Tim was talking about, more open-ended learning, like where kind of a lot of our problems we are tackling is like the prompt, the task is existing, comes from the human, or maybe kind of is some of these benchmarks that are out there. But it would be really interesting for the model to have some notion of uncertainty of what it doesn't know and try to kind of improve itself from that point of view, right? Trying to kind of gather more tasks and set itself different goals and try to achieve those and have access to tools to go beyond its starting point, right? From the kind of the data that it's been trained on. So that really fascinates me. And a lot of research that actually Jakob is also working on, like multi-agent learning as well, like not just collapsing into its own distribution, but in kind of interacting with other agents and trying to achieve goals. So that's also very fascinating. And I think there's a lot to be done there that we haven't done. And but I stop here.
Well, we've heard a lot of concepts and words there. I mean, it was mentioned about sample complexity, compression, uncertainty. These are, I guess these are all things that people in cognitive science have thought about. And so maybe I will jump David. We'll get back to the data in a second. I was wondering if Katie and Felix had thoughts of whether that had a role in, the next thoughts, ideas from cognitive science had a role in next generation AI.
I actually, an immediate response that I had to what you were just saying is sort of connected to the open-endedness, is that I see open-endedness, or the interest in open-endedness, as like a implicit response to the idea that all of our evaluations for AI suck. In the sense that they're highly variable given even one model and under certain conditions, and if you do certain adversarial attacks that are simple for humans to overcome, the model fails miserably. I think, for example, theory of mind is a great set of evaluations lately, that we have a paper coming out about this, about reevaluating these evaluations, where you can give the same model effectively two different evaluations that are supposedly testing the same thing, say false belief attribution, or knowing when someone believes something that's not true. And they'll perform completely differently depending on which evaluation you give them. But if the evaluation were truly testing the underlying ability, you would effectively see the same kind of results for either evaluation, and you don't see that. I guess more practically is that I think open-endedness is more about this idea of like, what's the right environment under which human intelligence evolved, right? And there's this like funny conversation I had recently with someone at OpenAI where they were mentioning that, oh, well, of course we're just going to scale up the compute. We are trying to approximate evolution. And then the immediate question that I asked them was like, okay, what's the training data? And then they're like, oh, we'll just make our own. I'm like, yeah, but how? Who's going to make that training data? And eventually the conversation came down to both of us saying, you're probably just going to hire a bunch of anthropologists, psychologists, and cognitive scientists to come up with that data for you in the first place. Effectively kind of taking the long way around rather than just doing the simple thing of maybe looking at humans first and then kind of going back from there. That's one comment. I'll let Katie talk now at this point, unless you...
I think kind of building off that of the environment, which Professor Preston also mentioned in his talk of kind of what is the environment that humans kind of grow in and collaborate with others. I think that there's, in addition to thinking about the kind of models themselves and the agents that might work with people, I think thinking about the ways that humans and AI systems work together in kind of broader multi-agent systems, as you mentioned, is a really interesting area. I think we've got a lot of great work in managerial sciences and operations research of thinking about teams. Like what is the future of teams of humans and AIs systems working together. I think that there's a lot of really cool work in that space that I'm excited about. And then getting back to the uncertainty point as well, I think I would encourage any young people to look at probabilistic programming. I've worked in Josh Tenenbaum's group. I think that a lot of people at MIT and now at Yale with Alex Lev and Tyler Brooke-Wilson who are there. These tools are getting much more scalable and efficient to do kind of differentiation in. I think that that toolkit is very interesting to explore in the next 5 years as a way to actually build explicit models that can kind of manage and express uncertainty in interesting ways.
Yeah,
so I'd encourage that.
Maybe to build on this kind of call to action is that if anybody's interested in this idea of AGI the human way, as Josh Tenenbaum would say, one way to think about this is that the problem is actually about scaling up the models that we already know explain human behavior at state-of-the-art levels. The problem is that they're intractable, inference is hard, training is hard, or learning is hard in these models. And if you could just figure out the scaling issue, I think that would qualitatively shift the kinds of AI models that we could build today.
Okay, well, let's have the
Okay, so going back to what Jakob said about 2 trillion tokens. So I don't disagree with him, but I would push in a different direction. So besides a simple language of differentiation and linear algebra that machine learning has gifted us, it's also gifted us a workflow, which is basically you have a data set, you have an objective, you have some competitive dynamic, like a leaderboard, and you have sharing of ideas or code. And that workflow has been insanely successful in a variety of domains. And it's sort of spreading in more and more places. So I see signs of chemists trying to build large public data sets, and a lot of this going on in biology and so on. And this workflow, it's basically the scientific method distilled, but it's not just distilled, it's also kind of a cartoon version of the scientific method. It's really, it's not even just the essence, it's a bit oversimplified, this workflow I just described. And, and then people get a bit crazy with it, and they say, why don't we just download the whole internet and train on it? And, anyway, I'm not sure the problem is the models. The problem is that this data, the entire internet is self-contradictory. There's all sorts of opinions in there. How can you expect anything to learn, efficiently from this giant mess? So I think a lot of work is going to be done, both with the sort of language model type stuff, but in all the sciences, all of them, to build standardized data sets. You can almost think of it as like railways. So it's not so much we have a hammer and we're looking for nails, we have a railway and we're looking for tracks. But we're not looking for them, we have to build them. So we need to standardize the gauges, we need to standardize basically how the data is constructed in such a way that it's useful and the models can be sample efficient. I mean, you can be smart about how you do your matmos and how you organize your layers and all this stuff, but fundamentally the problem's not there. It's in constructing coherent data sets, having them fit together well, organizing the world into useful categories before it gets to the machine learning models.
Do you agree?
Yeah, I just want to follow up on that quickly. I think you touched on something super important here, which is evaluation has sort of been a second-rate citizen in our community. Benchmarks have been these. It's quite ironic, actually. Someone said this on X recently. You have these, mega projects of billions of dollars of compute being purchased, and then you evaluate progress on benchmarks that some PhD student who hadn't slept in 5 days hacked up over a weekend, right? So it's really quite bizarre if you think about how much we're now using benchmarks to not just evaluate progress, but also guide how large corporations, large teams of people actually align themselves. What means progress? And once we take that point of view, that actually benchmarks are guiding where scientists put their thoughts and where corporates put their money, it's clear that we should think very, very carefully about what the metrics for progress are in machine learning. We're building the future of humanity. We should be very, very careful about what does progress actually mean. So I'm also strongly advocating, as part of this, think about the next step. Something that I think will be useful in the next 5 years, no matter what happens, is good evaluations and being very, very careful about what constitutes progress. Because I think this is obviously something where, if we don't measure it correctly, we could all be in dire trouble. And so the alignment community is the extreme end of that spectrum, the problems they think about. So I think I just want to double down on this, really thinking of, to some extent, creating the objective functions now that we're good at optimizing is the primary task maybe with somewhat of a researcher. Because probably in the next 5 years, you can automate the method selection, the tuning, and what is left is a specification problem, what constitutes progress.
So what would the sorts of evaluations you're thinking about? Things that are really testing hard generalization somehow?
Again, so the thing I pitched just at the beginning here, which is we should optimize radically for sample efficiency. Whatever we have that's like a gaping hole between machine intelligence and human capabilities at the generalist learning level, we had the learnability question come up earlier. Whatever those things are, let's make those front and center of our benchmarks, rather than saying the goal is cross entropy after 1 trillion tokens. That is not a realistic setting we should be optimizing for, but we have been as a community. And that makes sense because of the benchmarks and tone is being set by the very, very big players, and this plays to the narrative.
Yeah, I 100% agree, a huge plus one. I think there we have very clear metrics, let's say math or let's say some coding and stuff like that. I think there is hope that we can iterate quite quickly and kind of measure and have like very objective performance metrics, but in open-ended tasks or like where humans are involved, it's going to be really, really difficult. And actually, how do you measure based on what human feedback, like what kind of reward model are you going to be using? And this is just for evaluations I'm talking about. Like during training, you also have all of these questions, but that's going to be really challenging. I also think machine learning researchers are not great at this, and I don't think we have a history of kind of thinking about how we are evaluating this very capable system, but cognitive science has thought about it a lot, especially how do you measure behavior, how do you compare different models and kind of humans here. So this is going to be really interesting to know the perspective from that side and whether kind of there is any effort being done on that from that community to address this problem. So we have cognitive scientists here, so maybe you could tell us a bit more. Yeah.
I actually had a pretty reasonable suggestion for thinking about evaluations at even a smaller scale, which is a recent project that I was doing at DeepMind last year about instruction following. And this actually came from my frustrations working with Gemini pre-release on some automated software engineering stuff, just program synthesis, and it wouldn't listen to anything that I did. We gave it a tool palette, and it was just something like, oh, hey, download this GitHub repo. All the other language models would work to a reasonable degree to modify this virtual environment, download the repo. But when you ask Gemini, it would hallucinate the output every time, right? It no longer does this. It's good now. But the idea is that at the time, I was like, oh, this doesn't follow instructions. And of course, everyone on the team was like, no, no, no. It gets a good score on the instruction following eval. And I was like, okay, can I see this eval? And then, of course, you look at the eval, and it's missing some really basic components about the phenomenon of following instructions. And so I could say what the eval does, but I think the one way to think about this whole evaluation problem is to make it kind of simple. Just think about what you would expect for that phenomenon to be true within a system. What does it mean to have this ability to follow an instruction? What does it mean to reason? What does it mean to have theory of mind? Things like this. You'll realize, of course, first, really hard to answer a lot of these problems, or these questions, mainly because we just don't have a good set of theories about what these things are. One of the motivations for me, at least studying cognitive science, is to just figure out how they work in people, at least. But they basically imply a different kind of design pattern than what we're used to in machine learning, which comes from this area of regression and classification, where traditionally the problem sets are really well specified analytically, right? Dog, not dog, 1,000 images, you have your statistics, it's pretty good. But when you start moving on to things like reasoning, planning, et cetera, now the domain becomes kind of a little amorphous, sometimes uninterpretable. Oh, there's an edge case that works here, maybe not here. And it's hard to write down analytical solutions and thus hard to write down the proper evaluation. And so I think actually we should revisit design patterns for evals in the first place. But you could do it on a phenomenon basis, at least at first.
Okay, so I think it sounds like there's a general coherence that new evaluation metrics are going to be as fundamentally important to guide the direction of new research. But on a day-to-day basis, when you're doing AI research yourself, that's not really what you're thinking about. You're thinking about what new architecture should I do, what new algorithm, what data should I use to train my model? Like, what's the directions at those levels? Is there a particular level that stands out amongst the rest? Where's the most fruit going to be?
If nobody speaks, I will speak.
Go ahead.
That's the agreement we have, James and I, so you just have to bear with me. It's not my fault. It's because he told me this. So the only thing I would say is there tends to be like a end of history kind of sentiment in the community. I don't believe it's the end of history. But more so, if it is the end of history, there's not much to do in this case. So what I mean by that is, if indeed the current paradigm does lead to AGI and runaway self-improvement based on further myopic improvements, I mean, that might be possible. But then there's like, I don't want to have anything to do with it. It's a really boring history. Does that make sense? So I have to put all my eggs in the basket of trying to find the next sort of like big disruption and big curve. And I think we're really bad at predicting this. I was really bad at predicting this current revolution a priori. So anyone who's answering this question right now, I would just ask you, did you see this current paradigm coming? If you did, then please sit down and predict the next one and tell me about it. If you didn't see that coming, then maybe just acknowledge ignorance, that we don't know what this next big thing is. And we should probably spread our bets, and we should go after a few ambitious goals. But there are things that we do know, I think. We don't have to pretend complete ignorance. And one of the things is we're going from specialism to generalism. I think this will hold true. So again, if you're adopting some Gen AI model for a specialist use case, probably the work you're going to do in the next 5 years will be toast, like 99.99% of the work in our community has been. And this is fine because it's difficult to spot the 0.01% that will be useful in the future, right? But go towards generalism. Go towards things that if I give you an infinitely large computer, your method will be infinitely good. Now, that might take infinite time to get the infinitely large computer, but maybe scale that a little bit. It's a good rule of thumb for your project selection. And just be kind of insane. Right? Think about first principles. What is, in principle, the right thing to do? I love the probabilistic programming, by the way. Let's just scale up probabilistic programming. Who is doing this? Who is putting $1 billion behind making them faster? Well, nobody, right? Because not the myopic path of progress. Let's go. Let's pick 5 directions as a field, build benchmarks around them where these things actually are state-of-the-art, that measure something that is not the standard paradigm of self-supervised learning, where actually new methods can succeed and will succeed. Let's build those benchmarks. People will come. And the revolution will happen. And I'm quite surprised that academia isn't playing to that strength of actually setting up that that benchmark game a bit smarter, and instead is playing according to the playbook of the big players. I mean, I love the big players. They pay half my salary. Sorry, half my time, more than half my salary, obviously, because I'm academic and the rest of the time. Anyway, that was my way too long answer just to fill some time. You're all welcome.
Any responses from anyone here?
Yes, I definitely think probabilistic programming deserves more attention and kind of better ways to synthesize these generative models, these explicit generative models. I do want to push back a little bit on your question of what students should be kind of spending their time thinking about on the modeling side rather than the evaluation side. I do think, like we've just been talking about, that students should really be spending more time thinking about evaluation. I think thinking about evaluation interactively with people, ways that we can make evaluation more efficient. It's expensive to bring in humans to do evaluation, especially expert humans. Are there ways that we can kind of better automate and kind of make that process work more efficiently? I think that requires a lot of innovation and deep thought as well.
I mean, you can even think about some of the OG learning algorithms like Rescorla-Wagner, right? These were all kind of inspired by empirical observations by a lot of psychologists and neuroscientists back in the day, and then, converted into these algorithms that we use for a lot of things like reinforcement learning, backpropagation, et cetera, things like this, right? And so maybe there's actually a really strong argument, for focusing more on the phenomenon of interest for you as a researcher, where you're like, oh, it's interesting that people are really good at doing this, but O1 doesn't do it that well. I wonder why. And then going from there and building out algorithms and evaluations, et cetera, and maybe not in any specific order, but focusing on the phenomenon first, because it seems like a lot of the big progress has been made, at least historically, focusing on phenomena first.
Okay, I would say, I think it's a waste of time to try and predict breakthroughs. They just happen. We don't know. But what you can kind of predict is where solid progress will be made. And again, I think there's a huge amount of work to be done just systematizing data in the natural sciences, in engineering, in lots of places where it has not been done. This is like hard, good work that will obviously pay off. Somebody needs to do it, and by somebody I mean huge numbers of people. It'll pay off both in terms of just, there'll be benefits from better predictions about chemistry, better material science, it's a long list of benefits that are almost inevitable from the tools we have today. And also, there's a good chance that these are the places where new breakthroughs will come from, because machine learning spends a lot of time dancing around vision and language, but hasn't spent much effort on material science. There's new problems there. I don't know what they are, but once the data exists and is publicly available, people will have to think about it.
Just before then, I thought I'd ask if there's any burning things that you just want to release to the audience that we haven't had time to speak out that you think is particularly important. Go ahead now, otherwise we'll.
I will actually add one other thing on the modeling side that I think is really interesting and worth people working on. We spent a lot of time as a field thinking about kind of how we solve problems and deciding increasingly kind of which problem to solve. But I also think people can create new problems, new games. That came up in one of the questions earlier. I think that's really interesting of how is it that we can build systems and kind of better understand how we as humans create new problems, new games, new systems. So I think that deserves more attention as well.
Okay, perfect, thank you. Well, any questions from the audience? There's one here.
Cool. Thanks for the interesting discussion. I had a question for regret-based unsupervised environment design. I think one of the problems with reinforcement learning is the lack of well-represented levels or curriculums for the agent to learn. And I think early on, Michael Dennis proposed paired, which is a very theoretically sound method for discovering new levels through regret. And follow on, we have a nice trajectory of research in this direction from Pilar, proposed by Minchi, things from UCL, and Parker Holder in Oxford. I was wondering what's left to do in this field, and would that be an important problem to solve? I think it's well suited for tabular 2D RL environment, but I would be interesting to see if this could scale to some more sophisticated 3D humanoid scenarios.
Cool, I can take that question. For those of you who don't know about regret in environments, I'm sorry. I'm kidding. So it's basically a method where you try and optimize not just an agent to play a game, but you also optimize a teacher that finds settings that are hard to play for this agent. And why is this nice? Because in principle, you can learn to play all the games. And then if you can play all the games, you might be able to solve all the tasks. And it's one of these visions that sounds really cool if you hear about it, and then you start doing research on it and nothing works. And that's true. But we have actually made some progress where we've gone from nothing works until you can guess the hyperparameters using many, many samples correctly to things do actually work in simple settings. And I think the heart of that idea is the same thing that we discussed here. Task generation is itself a really hard task. And we've been kind of ignoring this because we've been assuming problems just get given to us, right? In some sense, the biggest lie in any reinforcement learning paper is the background section, where it says, I'm assume an MDP, right? What does that mean? I have given a perfect description of the problem in terms of transition dynamics, states, and actions. Turns out no one gives this to you in the real world. And this is something that really as a community, we've just been given. We're assuming, this is like saying, assume a cow is a point, right? Is a sphere, right? And then you do a bunch of stuff on this, and we've written tens of thousands of papers on this, right? And my key I guess, question to everyone working in this domain is, how do you get rid of this assumption, right? What is a reasonable assumption to make? And probably, probabilistic programs, assuming you get a random drawer of a task from the entire space of all tasks, right? What's the prior of all possible tasks? You can calculate the posterior given some observational data, right? This is kind of what we need to be doing, base optimal learning in that POMDP, in this partially observed setting. And then you can think about regret in that space. Does that make sense? But it's a very, very different setting. We have to basically move away from these really unrealistic setups where we've given oracle access. We can get trillions of samples. Because I think this was one of the big failures of deep reinforcement. Can I show a show of hands who knows reinforcement learning? Deep reinforcement learning. Cool, those of you who don't know, it used to be the future, right? We used to think it's the future again, actually, you're right. Right? and really, we got really good at playing games, but we got really not good at doing anything else with this. And one of the big issues was we assumed white box access. So moving away from this, regret is one option, but I don't think it's a final answer. I think it's a good area to work on. Generating tasks is itself an important machine learning task. How do we benchmark around this? Because you build the benchmark, they will come. We don't build the benchmark, they will not come.
So let me add to that, actually. We actually scaled the prioritized level replay that you're talking about. This is when you basically simplified, you have a lot of tasks, and you want to learn from the ones that gives you the most signal at the moment, because you don't want to learn on things that are either too easy because you already solved them, or they're too hard and you shouldn't be attempting them right now because otherwise you're just learning zeros. So actually we scaled that to a very, very large environment, like 3D with multi-agents. This is called adaptive agents. And it was really exciting because we took these methods that are as you said, designed in these tabular settings or very simple environment, but these ideas actually scaled at that level. We didn't change the method at all, we just applied it. And it was really, really exciting to me because it showed that we could translate and bring some of the ideas that are studied in these very small settings if they're assuming that at a scale they're going to work. So there are not assumption built into the nature of the method that would not let it to scale. So that's actually really interesting. And this curriculum learning that you mentioned, I think is going to be really, really important going forward with kind of learning harder and harder tasks for all of these, like even foundation models, in my opinion, because you really need to decide what data to learn from, and both because learning is expensive and also because you don't want to kind of learn on things that are too hard, that are not giving you any signal, or too easy. So definitely a very exciting direction to pursue in academia. If people are interested.
It's awesome that you scaled this. So what real-world application can we do now that we couldn't do before?
What do you mean?
I'm just, it sounds like we made a lot of progress. So what can we solve now? Where can we do things now that we couldn't do before that isn't playing games? And I put this sort of ADA task still under games.
No, absolutely. It is definitely games. But I think it shows that these methods can scale. So in the game setting, I agree with you. I think it's hard for me because like when I kind of personally studied ADA, it was not because it was a game. It was like I wanted a very complex environment that kind of I could test this hypothesis. Because, we can go to the real world, right? But the real world is expensive, it's very slow, and some of the things we can actually study within simulators, in my opinion, that are kind of let us kind of iterate much faster. So I would push back a little bit against like too much like, no, games are not good. I mean, games, if you are aware of the assumptions you're making and you're aware of kind of what are you hoping to transfer from this. If you're hoping to go from the game and take the trained model and put it in the real world, it's not going to work, right? Like 100%. But if your question is, I want to test this learning method, and I know that I'm making assumption that the reward model is given, or like is perfect, then you can actually study these algorithmic questions very well, in my opinion. And then if you know in the real world your reward is noisy, okay, add noise to your reward, or maybe you want to learn about what is the nature of the noise in the task that you're interested in, and try to mimic the noise in the system, etc. So I kind of a little bit push back on that, but at the same time I agree, like kind of we did all of this work and it was really exciting that you see kind of adaptation and transfer, but if you take that policy and put it somewhere else, it would break, right? But I do think for me, it answered a lot of questions. Oh, actually, we can scale deep reinforcement learning using the curriculum, because without the curriculum, we couldn't actually see any scale, we couldn't see any adaptation. So that tells me that, okay, if you're in a vast space with a lot of tasks, you need some form of curriculum to take the agent through. Otherwise, it's going to be very difficult to see any signal. And then again, you can then bring in task generation. So that answer we didn't answer, right? The task came from the environment. But anyway, I mean, we can go on and on.
No, I just want to say, James also asked me to stir the pond a little bit. And
no, thank you. I like that.
Can I push back on something that you actually
I certainly did not.
I'm going to stir the pond a little bit more.
Please.
So you said a one sentence thing that I think actually is indicative of a lot that's being said in the AI space right now, which is like, oh, if we find out that the world is noisy, we just add a little bit of noise to the reward model, and like. That's actually not exactly true, right? It's not just adding noise. It's like, okay, what kind of noise?
Absolutely. So that's what I was saying.
Right. So going to this question about just bringing it back to the idea of like coming up with problems, or this idea of play, right? There's this postdoctoral scholar at Stanford, Junyi Shu, that I'll just like plug in here, has this like beautiful work on studying play in children. By the way, if anyone's interested in this, they should definitely look at developmental psychology, because it's like, this is what kids do all the time, right? And they have some unpublished work right now that they did in my lab, or Tomer Ullman's lab, and the idea is that they basically contrasted the different kinds of games or different kinds of perturbations on a world that people could play in between LLMs, all sorts of LLMs, and people, all sorts of ages. And it turns out not only are they different, but the way that they're different is qualitatively different. So LLMs will have these particular modes of suggestions. Well, they'll only suggest particular variations along certain dimensions of the room or the rules of the game, et cetera, whereas people are highly variable, but in a systematic way, right? And so one thing that's interesting is that in the AI space, it's often the case that, and I'm not saying exactly you said this, but what I often hear is that people will sort of find some discontinuity between what their model is doing and what it should be doing, and say, oh, I'll just add another parameter to the loss. I'll add another coefficient to the noise, something like this. And that's fine, and it does push you a little further on this evaluation, but we already know that evaluations themselves are kind of troublesome. And so it's kind of like almost like we're just sweeping all this dirt underneath a rug and just hoping no one notices it to some extent, right, until we kind of release it at test time. So I guess the point that I'm trying to say here is just sort of, it's good to sort of think more theoretically and first principled about exactly what kinds of things we're doing to these models and why, right? As another side note, the probabilistic programming frameworks are one of the only classes of models that explain how humans actually generate these games and these experiments. So that's another thing to say as well about PPLs, but yeah.
Okay, I think we have time for one more. Why don't we go over here?
Thank you. And there's a sense from what you're all saying that there's a limitation in the development of AI capabilities because of our human capabilities and the frameworks that we work with that lead to biases. And I was wondering what your thoughts are on how we get past that, or how we go beyond.
Can I say something? I don't mean to take up the space here. If anyone has anything. Okay. What you said actually was a great suggestion. So Rory and I have been chatting about this quite a lot lately, but one way to get over this is just to put resources in other places. So if you look at all the big three, the huge AI companies right now, they all do very similar research. Obviously, people inside the companies will tell you it's different, but the fundamental commitments of the mathematics, the operations that are basic to each of the models, they're all shared, right? And they're actually all intertwined, right? Like people leave DeepMind to go to Anthropic to OpenAI, and then it's just this like circle that keeps going around. But there are completely different model classes that might have, of course, like symmetries with other, probabilistic programs are similar to neural networks in some mathematical sense, and they're exactly the same in certain places. But practically speaking, they do different things, and they lead to different kinds of behavior, right? And so I think if we could put resources in, basically, if we could have people who have the resources bet on different kinds of research programs through, academic endowments, startups, et cetera, I think we would start to see a lot of this mold start to break.
One more suggestion on this, and I'm kind of reiterating, which is the current paradigm is infinite data, infinite compute, infinite samples in a simulator. That's where we evaluate algorithms. And that's not what any of the world looks like for most practical problems. It looks like this from the perspective of some very, very specific players in the field. And my claim is, if we construct benchmarks where these models are systematically bad, then resources will follow. We have to create the benchmarks to actually measure things that we care about as a society. So for example, how good is your reinforcement learning algorithm at operating a sewage plant? That's not like playing Atari. It's quite different, right? You don't get 1 trillion samples, you only get offline data, and the dynamics are complicated and done. Does that make sense? And we've been really not very, very good at asking other things we're measuring, actually the things that we care about as a society, right? How good is my bot at supporting a medium-scale business that has 1 GPU and has 1,000 customers? And the biggest data set I'll have will be like 10,000 data points, right? These are not the benchmarks that we've been pushing for in our field. And I think the way we get back control is by getting back control of the benchmarks. And all the resources will follow the alignment problem, I think, can be addressed partially through just better benchmarks.
There are some benchmarks that people have made, for example, the ARC benchmark by Francois Chollet.
Which real world problem does that correspond to? Why do I care about this funny pattern? If I'm a small business owner, why do I care, right? Why don't we take the problems that people actually care about, where progress corresponds to progress for humans as we know it?
So I want to be a bit of a devil's advocate here. I 100% agree with a lot of things you're saying, but I want to also take a different, let's say we all care about, better, I don't know, we can, for the AI to solve the next conjecture that is not solved, or I don't know, cure cancer,
I don't care,
right?
do my taxes.
No, just wait. even your taxes, let's say even your taxes, right? But if everybody thinks about solving that problem in the whole complexity, right? We can't, if I'm starting as a PhD student, I have my computer, and I'm gonna think about solving kind of this very difficult problem. It would not, it would make no sense, right? I'm just saying we need benchmarks on the way to, we need to split kind of directions in terms of what we are pursuing. And some of the aspects of the problem can be simplified and tested in I agree that we should be very careful that, our goal is there and not kind of fall in love with, now I'm only about the games, right? But maybe you can answer some question in a much simplified setting than just tackling the direct problem. But I'm just saying you need to be aware that, the assumptions I'm making, can it kind of go beyond the setting that I'm studying and kind of keep the kind of goal in mind. I just don't understand this kind of perspective where we should just think about these very hard problems and everybody focuses on that. I think that is a little bit of, I don't know, maybe you can expand on that.
You know, I don't mean we should all work on my taxes. Don't go. But I'm saying if we actually think about what problems, what capabilities do you want to have from a societal point of view?
Yes.
What do we want these systems to be able to do in 5 years' time? And what proxies of tasks actually correspond to this? I think we'll find it's very, very different from the places where machine learning people put their brains behind.
That is
and that's because the current benchmarks, you can just import the benchmark, run your code, and write a paper. And I want it to be as easy as that for someone to say, I care about this problem, or collection of people cares. Let's generate a benchmark for it, and let's make it very easy for someone to get started on, for example, automating tax returns, or, for example, optimizing traffic flow, whatever it is that we care about as people. I think that's a narrative we've really not taken control of.
I agree. There's less emphasis on that for sure.
Okay, well, I would love to keep talking, but I believe that we are, I believe there's some schedules we have to abide by.
How unfortunate.
So I want to thank everybody here for not only their phenomenal input, but also their desire to sort of be up for a debate. So thank you all for being here.
Yeah.